the heating continues, a little bit of water begins to splash out of the glass tube. This causes the water in the flask to suddenly start boiling. This resulting force causes hot water to spurt out of the glass tube. The same phenomenon occurs in geysers. What happens at that critical moment? In fact, before the eruption, the water inside the glass tube exerts enormous pressure on the water inside the flask. This pressure raises the boiling point of the water, so the water doesn't boil, though the temperature exceeds 100 degrees Celsius. As the water continues to be heated, the force becomes great enough to eject some water. The water in the glass tube falls and the pressure in the flask drops, so does the boiling point. When this happens, the water is already hotter than 100 degrees Celsius. It instantly turns to steam and water blasts out in a boiling eruption. When water becomes steam, its volume expands 1,700 times. The force of this propels the hot water outward. Long, narrow fissures and a subterranean reservoir create a rare and unique geology. Wherever ample groundwater and geothermal heat are added to these factors, a geyser is born.
It's a very unique situation. It's just a freak of nature that all of these things line up and allow it to happen.
A narrow tube and a flask heated from below. Unless you have the natural equivalent of that, you don't have a geyser. So there aren't that many of them.
It's strange that it must be over 100 degrees Celsius.
Yes, it is. That is because water deep below the surface is under higher pressure. Therefore, it has a higher boiling point. That's why it doesn't readily boil. Even if the water depth is only a meter, the boiling point rises by 3 degrees Celsius. Water 10 meters deep has a boiling point of 120 degrees Celsius. Let's take a closer look at Pahutu geyser erupting. We took some thermographic images of the hot water spurting out. Now, the water can be superheated to 103 degrees Celsius. Now, that's the white area. Hotter than 100 degrees Celsius, but not yet boiling, it surges from the ground. We can assume that deep underground, the water is heated to even higher temperatures.
I often use a pressure cooker when cooking in order to shorten cooking times. It's very convenient. A pressure cooker allows the water to reach a higher temperature.
So you're familiar with the concept?
Yes, I am. It shows you the power of water. Just boiling it can produce a spectacle like a geyser.
When water is vaporized into steam, a huge amount of pressure is generated. At the time of the Industrial Revolution, we learned how to use this in steam engines. In fact, harnessing steam power was one of the things that made the Industrial Revolution possible.
A New Zealand geyser has shown us the power of superheated water. For our next spectacle, we travel to Zao in northeastern Japan.
The Zao mountain range runs through Miyagi and Yamagata prefectures. During the winter, its trees become cloaked in pure white. This is soft rime ice. It may look like ordinary snow, but it's not. In the entire world, it is only here in Zoao and at a few other spots in Japan that so many soft rime trees like this can be seen. How does the soft rime ice form? November, before the soft rime ice forms on the forest. The mountain slopes are forested with a species of tree called Mary's fir. Branches dense with small needles provide a platform for the soft rime. In January, soft rime forms quickly. The forest is transformed as the green trees are swallowed up by white ice. A close look at the surface of the soft rime reveals a remarkable pattern. This pattern covers the entire surface of the soft rime. Locals call it the shrimp tail effect. How does this pattern form? We spent a night filming the branches to find out. It was minus 13 degrees Celsius and the wind was blowing at 10 meters per second. Even though no snow is falling, an amazing phenomenon occurs. Suddenly, white ice begins building up on the surface of the needles. As it grows, the shrimp tail pattern appears. The wind is blowing from the right side of the screen. The white buildup grows on the upwind side. So what is happening on the tips of the needles? It's time to get the microscope. A Mary's fir needle is set under it. We zoom in on the tip. The entire setup is brought outdoors in an effort to capture under a microscope the moments when soft rime forms. The crew endure roaring winds for 30 minutes.
It's unbelievably cold.
The shrimp tail effect is even appearing on the crew. What do we see through the microscope? Even when no snow is falling, tiny crystals of ice 1/50th of a millimeter in size form on the tip of the needle. Analysis shows that tiny water droplets fly in from the right side of the screen and turn to ice when they touch the needle.
The shrimp tail effect is caused by a stream of flying water droplets that freeze instantaneously, one after another, over and over again. On the upwind side, the ice continues to accumulate. A huge amount of soft rime forms.
But the droplets that form soft rime ice are no ordinary water. Here is a plastic bottle full of the same kind of water as the droplets. As it is poured out,